we're going to see here today is a lab experiment with conservation of momentum and also impulse momentum. And so one of the confusions is when do you use each type? So we'll see how that actually works here. What we're going to notice is that we're going to have three different examples. And in our first example, we're going to have a system, and the system is just going to consist of the cart that has more mass. There'll actually be two carts on the track, and you'll see it here in just a second. The goal is to find the average force exerted by the stationary smaller mass cart on the moving larger mass cart. So we're going to see what that actually looks like here. So in our two cart system here, we actually have a cart that has more mass on it, and it is going to collide with the cart that has less mass on it. What you'll notice is that we always want to make sure that our track is level. So here we can see that we finally have it leveled out, and we're going to record our data here. And so what our goal is to try to figure out, as this cart collides, it's slowed down, so its momentum changed, and the question is, how did its momentum change? And so we're going to look at some analysis on the LabQuest to get that information. Okay, I'll have the data set that we have available from this experiment here in just a second, but what I'll point out is that you'll have something that looks like this, a position time graph, and the cart's moving. And so if we take this region of it and look at the slope of this, we'll be able to figure out its velocity. And so we can go through and do that by going through Analyze, Curve Fit, choose the position function, and then choose it to be a linear function. And the slope of it would be the velocity of this in meters per second. This is not actually the data that I used for this experiment, so I'll show you that here in just a second. But the other thing that we're going to pull off of this graph is the amount of time of contact that was incurred. And so the time that it incurred was from this point of contact until it comes down here and then becomes somewhat constant velocity again. So we would record this time point over here and this time point down here, and that's the compression of the spring that we have. And this is the data that we would end up with. So the mass of the larger cart, which was moving, the initial velocity of the larger cart, and then the final velocity of the larger cart. So the momentum actually lessened for that cart, and so since that momentum of that system changed, there's a force that's causing that. And so the goal here is to find the force from the impulse, and so this is an impulse momentum problem because the second cart is outside of our system, causing a force to be applied to our system, which was the larger massed cart. So the goal now is to actually go through and try to find the force exerted by the second cart onto the first cart. So you definitely need to go through that process and find the force using impulse momentum. You won't actually use the mass of the smaller cart on this one. So take a second to do that. On our next problem, we're going to look at the system as being both carts together. And the goal is to determine how well conservation of momentum applies. So even though there's actually going to be a spring mechanism inside of it, there will be forces applied. That force will actually be an internal force. So what we're going to do is we're going to take the momentum of the one without the spring as exact. That'll make a little bit more sense when we look at the situation. And we're going to trigger the spring with the velocity actually being 0. So in our setup here, what we'll have is we'll have our cart system. And what we'll have is a spring inside of the two, pushing them away from each other. So this is our setup, and we'll have that spring pop out, and the two will fly away from each other. One of the things we have to realize is we have different sensors. So for this sensor, that way's positive for our system. And for the other sensor, the other direction is positive. When we release them, what we'll notice is that whenever I push down on that release mechanism, I'm actually affecting the velocity of the cart. So we need to do a little bit better job on that. So even trying to touch it quickly, I'm still pressing down on it. I'm slowing that cart down, so we don't want to do that. And so maybe we use some other mechanism. in order to get a cleaner release off of that. Again, our system here is actually both of them together. So even though there's actually a force that's being exerted, that force is actually inside of our system. So this is going to produce an internal force. So that means that our conservation of momentum will hold. The results that we had are two masses that we have, the mass of the larger cart and the mass of the smaller cart. And what we end up with is the final velocities of each of these. We have to consider one direction positive, the other direction negative. Again, we would get those off the slopes from the LabQuest. The initial velocity of the system is 0. And so what we're going to do is we're going to take a look at how one momentum changes on one cart, cart A, and how the momentum changes on the other cart, cart B, and compare those. So this is a conservation of momentum problem. There's no impulse that we need to consider there. Whenever we're comparing them though, what we're going to want to do is we want to take the momentum of cart B as being the exact momentum. And the question here is, why do you think that is? So momentum B is the one that did not have the spring mechanism in it. So you can go through and do that calculation, conservation of momentum. And whenever you compare it, we're going to compare it back to the momentum of B. Our third example is going to involve an air track with gliders. We're going to actually include, again, our system as being both gliders. And the goal is, again, to look at conservation of momentum in a collision involving an air track. We're actually going to use photo gates for this. And so in order to set up the photo gate, we're going to go into the LabQuest for photo gate timing and change it from the default, which is the vernier picket fence, to the user defined, and the length of the cart is 5 inches. And we're going to end the data collection after 4 events, and we'll explain why that actually needs to be the case in just a second. So for our air cart situation, we have our photo gate set up, and what we're going to do is we're going to send along, and you'll notice that it has very little friction. As it goes through, it's going to block the photo gate, and it notices whenever it starts the block and whenever it stops the block, and the length of that blockage is 5 inches. So as we move them together, they'll collide, bounce back, and we want them to come through the gates toward each other and then away from each other. And so what we'll notice is that photo gate, whenever it comes through, it's going to block twice, or it's going to block and then unblock, and then block and then unblock. Those are the 4 events that we have. So sliding them through each other, they'll collide. We have to be careful about direction with positives and negatives as we consider those. Again, this is a conservation of momentum problem. And so the data that we ended up getting off the LabQuest, it gives us time intervals that we have, or time instances that we have. And on the LabQuest, this is actually in the listing from the chart. So not the sensor reading, not the graph reading, but the chart reading. And so for the lighter massed object, we have the time value of 0 whenever it begins to be blocked, and then 0.335 seconds whenever it switches to unblocked. So that's on the way as they're moving toward each other. And then similarly, as they come back through 1.8 and 2.033. So these are the 4 time events that we set. So whenever we set it up, we said we want to record for 4 different events. That's the 4 events. The other photo gate grabbed these. So we know that the length of each of those is 5 inches. And so knowing that with some very simple equations, we can figure out how fast it's moving, both as it's moving toward each other and also as it's moving away from each other. So we need to be very careful of the direction. This is a conservation of momentum problem, a classic conservation of momentum problem. The length of each cart is 5 inches. The mass of the lighter one's 180 grams, mass of the heavier one's 290 grams. The time before for the light was 0.335, and for the heavy was 0.2998. So I went ahead and subtracted the time intervals that we needed on the previous page. And then afterwards here are our light and heavy time intervals. So you can see here that it begins to be blocked here and then it clears here. And so you'll need to figure out those time intervals as well. So those time intervals will be used in conjunction with the length of the cart to figure out the velocities. And then we want to look at the momentum before and the momentum afterward. Whenever we look at this, we want to take a look at our percent error. And if we look at this truly as a momentum before and a momentum afterward with this set of data, we should actually end up with less than 1% error on this. And again, we're comparing it to what we started out the momentum with. That's our comparison state there. So looking to see if any momentum was lost as a part of the collision. So those are three different examples. We have the distinction here between an impulse momentum problem where a force is an outside force, and then conservation of momentum problems where there may be forces acting, but that is inside of our system. So go through those and see if we can figure out our results on them.